Hey, welcome back to CE 528. So we are picking up where we left off last time. We are picking up the discussion from transportation supply now. We talked a lot about travel demand in the last lecture. So we talked about the typical travel demand model forms and how we can estimate elasticity if we knew the model form. And then we talked about aggregate demand. Aggregate demand is essentially adding up all of your individual demands. And then now I want to talk a little bit about transportation supply. The classic supply curve is a model of production as a function of price. So the classic supply curve accounts for the fact that as the prices rise, the providers of service have an incentive to provide more services or more products, right? I mean, if you can sell something for more expensive, there would be more providers in the market. And that's the idea of the classic supply curve. So supply curve will be something like that slopes up. As the price goes up, there will be more suppliers in the market that will start to provide more supply. Now, and how is that classic economic supply curve? But if you try to apply that concept in the realm of transportation supply, you interpret that as the throughput provided as a function of price, and your price is essentially perceived user cost, or perceived cost is a function of flow. So transportation supply curve, you can think of transportation supply curve as your average cost function, because what you're saying is that a price or the perceived user cost as a function of throughput. And I'm going to show that with a chart. And in the next lecture, when we start talking about how the transportation supply and demand sort of work together, then that can give us, like, what's the appropriate price, where the equilibrium might happen, and so forth. And as with travel demand, price is not always expressed in terms of dollars, but it's sometimes expressed in the form of other impedance measures like trip time, the total travel time, and so forth. And then, as with demand curves, many underlying service attributes are assumed to be fixed. So when you translate your classic supply curve into a transportation supply curve, you have to fix many underlying service attributes, like we talked about: comfort, security, crowding, and all of that. So we assume some of those attributes to be fixed, just like we assumed for the demand curve. And then this supply curves, it looks the same way. The supply curve looks as it looked, and we've seen the supply curve, right? We've seen that supply curve in the past. So there is like a fixed cost at the very beginning. And so that's why the supply curve starts at some point higher than the origin. And then as you produce more output, your cost goes up. And you can think of that supply curve. And you must have seen this supply curve when we do, so let me go ahead and annotate here. So when we try to do, if you recall, so this supply curve should remind you of link performance function. Does anybody remember what was link performance function from CE 321? Does anyone remember link performance function from CE 321? And this is our introductory transportation class. We talk about that. Link performance function is essentially the supply curve. Do you remember what it was? It related travel time on a link of the network with something. It was a travel time on a link of the network as a function of some quantity. Remember what was that quantity? This is one user's travel time on the link of the network as a function of, nobody remembers it from 321? I'm going to go ahead and pause it for a second then. No? Okay. So that's all right. So, but the idea is that this supply curve is essentially your link performance function, or what we used to call volume delay function. Yeah, but as more people get added to the network or to the link, the travel time actually goes up, not down. It goes up as you add more people. And that's exactly what is happening here, is that the price, the perceived price of being on the network in terms of travel time goes up as you serve more and more people. So as Q goes up, or as the volume goes up, the travel time on that link goes up. And in fact, you can see that in a classic transportation way, the travel time doesn't rise very fast at the beginning. So you can see as you're adding more and more people this way, as you're adding more and more people this way, the travel time only goes up marginally at the beginning. But as you try to tend to reach capacity, see what happens to travel time. It rises sort of very, very fast. So that kind of gives rise to our exponential volume delay function. Okay. And then obviously, as the price rises, the demand tends to go down, right? As the price goes down, the demand increases, but as the price rises, demand goes down. So you have that backward sloping demand curve. And then based off of that, you can find the intersection of the supply and demand curve. So that sort of becomes your equilibrium for any link like that. So your link performance function, or the volume delay function, is your supply curve. And we talked a lot about the demand curve earlier in the lecture, and that's the downward sloping demand curve from here. So this is your downward sloping demand curve, and then this is the volume delay function, or the link performance function. An intersection of those gives you what we call the equilibrium point. It's a transportation supply and demand. It's an equilibrium seeking model, which expresses travel at the intersection of average cost and the corresponding aggregate demand curve. Okay. So for now, I think this is sufficient discussion about this. But we'll come back to this discussion when we talk about congestion pricing, and we'll come back to this discussion in the next class when we try to talk about, sort of consumer surplus in terms of the reduced travel time and so forth. Okay? So are there any questions about this? Any questions? No questions? So now the question is, if you know your supply curve and you somehow move the supply curve, right? You move the supply curve. So what happens if you do move the supply curve? So in the short run, when you do move the supply curve, so this S1 used to be your original link performance function, and now you made some improvements to your network. And let's, for the time being, you say that, yes, okay, maybe you added a lane, or you did something to your network that brought down the supply curve in the short run. And the supply curve became now S2, what it used to be S1. So not only is the initial travel time lower, but also at any given demand level now, the price has been lowered to this value. Okay? So you could see that if the demand stays at Q1, now the travel time would actually go down. Okay. Now, so what happens then is that if you create a new supply curve and your demand curve remains the same, now instead of having the equilibrium demand at Q1, your new equilibrium demand will be happening at Q2, because as you move down the supply curve and your demand curve is still at the same level, in the short run, now your equilibrium exists at a higher demand level. So this is what we call sort of the induced demand by lowering of the supply. By lowering of the supply, you don't remain at Q1, you now operate at the value Q2. And so instead of but your cost of traveling on the link is still lower, at least in the short run. But in the long run, it might induce the demand even more. And then, you go right back up into the congestion issue. So in the short run, yes, you can, even with the induced demand, your price of traveling. So remember, the original price used to be, here. Your original price of traveling on that link used to be here. But even with the new supply curve, even a little bit higher demand, now at least the price of traveling on that link is lower. But obviously these types of supply curve don't hold up in the long run, because sort of your demand curve shifts. And now there is like a whole new level of demand that might come in, because widening of the roads might encourage people to build more housing away from the city center, and people live more farther away because of this short-term reduction in the price of the travel. But in the long run, the induced demand may become even higher, and that might push up the price. So maybe the induced demand might lead to sort of a different demand curve completely. And if the demand curve changes completely to this level, the new price could even be higher than the old price. So you might be operating, if the demand curve shifts over time, you might start operating at an even higher supply curve in the long run. So this is sort of your long-term demand. So this is a long-term shift in demand curve, might push your price of traveling on that connection or that link even higher. So that's the idea of sort of induced demand in the short term. The induced demand, even with the induced demand, you could lower the travel time, right? But in the long run, because you encourage development farther away from the city by adding lanes to the network, you might actually push the demand curve higher, and then that demand curve might lead to you or the travelers paying even higher cost in terms of perceived travel time on that same network, even in the case of the new supply curve S2. Okay. Any questions about this? Okay. So now kind of that brings me to a homework problem. So there is a homework problem on elasticity, but I also have two additional homework problems. So this week's homework is not just one problem on the slide, but you have a total of 3 problems. So I'll just kind of make sure that I give you that message. So a total of 3 problems on the homework. So make sure that you look at all 3 problems. I have one here that directly links with elasticity and all these issues, but there are 2 more additional problems that you need to work on for the homework. And I'm going to go ahead and start recording. So we are starting a new lecture on cost modeling and pricing principles for CE 528. And I've told you that cost and pricing are related concepts, but they're distinct concepts. And a lot of times, cost, we want the cost to be pricing to make sure that the supplier is not gouging us or whatever. But pricing really depends on costs as well as demand. And it doesn't depend on cost as much as like you think that the supplier is going to charge us what it costs them directly. But if there is competition in the market, then supplier may be forced to charge what it costs. So that's one thing. However, sometimes if there is like, if they have monopoly going on, if they don't have any competition in place, then they can charge whatever they want to charge based on the demand for the product. Okay, so pricing and costs are related concepts, but they don't always sort of go hand in hand completely. Okay? So it's important for us to understand the pricing principles independent of cost, but also understand what does cost look like for any kind of supplier. So we have to look at both of those items before we can, think about, what should be the price of any goods or service. So what we're doing here is that we are trying to learn some pricing theory pertinent to transportation system. We'll cover some general pricing principles and then specifics of congestion pricing. And it is one of the key elements in today's debates regarding future transportation policy. So there are three major pricing strategies that one could consider. One is maximizing profit. The other is maximizing revenue. And then the last one, that's maximizing net social benefit. And you could sort of think about two ideal market types. One could be perfect competition, where you have low barriers to entry and anybody can join the market. And then the other one is the monopolistic pricing. Monopolistic pricing, where you don't have, competition at all. In case of traffic systems with mostly fixed infrastructure capacity, where you cannot just willy-nilly add capacity, we see some other pricing strategies in play as well. And they might include maximizing of throughput in terms of vehicles or people, raising revenue. Usually for transportation improvement, you want to raise revenues. So you want to maximize your revenues. And then create and preserve travel options such as high occupancy vehicle lanes, that you want to incentivize people to drive with more than one person in their cars. So then, you look at high occupancy vehicle HOV lanes as like, you want to provide that kind of option. So that's kind of like a pricing. And then you can look at HOT lanes, high occupancy toll lanes, that if you're high occupancy, you can go for free. But if you want to go as an individual or single occupant in a car, then you pay a toll. So differential prices for differentiated services. And that's one example of that would be HOT lanes, the hot lanes. So let's talk about pricing in perfect competition. So what do we mean by perfect competition? The conditions of perfect competition might include a large number of suppliers, each supplier trying to maximize profit. No single supplier can dominate prices, and transactions being costless means you can figure out what it's going to cost you very easily, and you have that information as a consumer available rather easily, and consumers have perfect knowledge of their options. And if you make one transaction with one provider, the next transaction, you're not tied to that same provider. So transactions remain costless. In transportation, these assumptions came true, close to being true for airlines, taxis, especially with the arrival of Uber and Lyft, TNCs. there is that competition between taxi and the and the airlines. Obviously, that's true in airline industry. A lot of competition there. Okay, so so let's see what happens in the case of perfect competition. So the assumed goal of suppliers in the case of perfect competition is that we assume that the suppliers, they want to maximize their profit. Okay, so their idea is to, how can we charge, how can we make maximum amount of profit? How can we make most profit? Every supplier wants to do that. So if you think about every supplier and the equation for their profit, the equation for the profit is pretty simple. It's the revenue as a function of quantity supply. So I'm gonna write some things down here. So my Q is quantity supplied. Okay. And my R is revenue. Revenue, and obviously revenue is a function of how much quantity are you going to supply. And then C is the cost of the supply. Okay, C is the cost to the supplier. And then cost could also be a function of Q. So both R and C are function of quantity supplied. So your profit equation is the revenue minus the cost. So R minus C, and R and C are both function of Q. So if you want to maximize this profit equation, and how do we maximize something? We take the derivative of that function and equate that to 0. Because remember, if you just kind of look at any function here, so if you draw any kind of graph, right? So if I draw any kind of graph, and this is, let's say this is the function P, and then this is Q. So not P as in, so not P as in price, I'm sorry. So let's say this is the pi function that I'm talking about. So let's call this function is on the y-axis, and this is the sort of the function that defines it. And then this value here is Q on the x-axis. If I want to find where the P becomes maximum or minimum, because I'm looking for maximum, I should probably erase this and draw a function. And if I want to maximize this function, I want to basically find this point right here. And this point, what's going to happen to the derivative of this function? What should happen to the derivative of this function at this point right here? Any ideas? Right. So this is from your calculus, is that if you want to maximize a function, we want to make sure that our derivative is exactly of that function is 0. So that's exactly what I'm doing here. I'm defining the profit function as RQ minus CQ. And then I take the derivative of this function with respect to Q. So my dr over dq minus dc over dq has to be 0. And remember this dr over dq. If you take the revenue, the derivative of the revenue function with respect to the quantity produced, that becomes my marginal revenue. So it's the extra money that I bring in by selling one more unit. And then DC minus DQ is the cost that I incur when I produce one more unit. Does that make sense? So this means DR over DQ is my marginal revenue. DC over DQ is my marginal cost. Because the derivative of the profit function has to be 0 for me to maximize profit, That means that my marginal revenue has to be equal to marginal cost in the perfect competition environment to be able to maximize my profit. My marginal revenue has to be equal to my marginal cost. So this is an important condition for how firms will operate in perfect competition. Now, let's look at this graph in perfect competition. And remember, in one lecture ago, we drew out some charts of market marginal costs and so forth, right? Do you guys remember that? And then I had the average costs and all that. Now, what do you think is marginal revenue then? So marginal cost obviously is it will be a curve that we drew before. The marginal cost started out at infinity if you had some fixed cost, and then it came down. So this is what the marginal cost curve looked like. So marginal cost curves, I'm going to try to highlight it here. So this is my marginal cost curve. Okay. But what is marginal revenue in this curve? What is marginal revenue here? So we figured out that, you know, this curve that I have on the next slide is my marginal cost curve, because that's how much it takes for me to produce one extra unit at any given output. That's how much it costs me to produce that extra unit as a supplier. My question to you is, what is marginal revenue? Yeah, revenue that you gain from an additional unit, but what do we call it? Is there a different term for that? I'm going to pause the recording. So yes, it's the marginal revenue is the revenue that you generate by selling extra unit. And that's nothing but unit price. Is the marginal revenue. Anytime you're discussing anytime you're talking about unit price, that's what the marginal revenue actually is, right? That makes sense? And remember that price doesn't really depend on the cost. Cost comes into play to decide, to dictate whether or not you can stay in business or not. Right? That's the problem. So, and then the price, but price doesn't actually depend on you. Price depends on the elasticity. Price depends on what's happening in the marketplace. So I'm showing you two more curves, two more cost curves in this chart. One of them is the average cost, just the variable cost, not including the fixed cost. Remember, when you don't include the fixed cost, you start your curve, average cost curve start at the same place as the marginal cost curve. And then this is what it looks like. So this is average cost curve that I'm going to annotate just now. Maybe purple color. So this is my average cost curve. But if I include my fixed cost, the cost of building that factory, then my average cost curve, that total average cost curve involved this orange curve. So I've got average cost, just the variable portion, and average cost is the total portion. And remember, the average cost total curve starts at infinity and comes down. Remember that from our previous lecture. Right? Now, if your market cannot clear a price of P prime that you see on the chart here, if the market cannot clear the price, P prime, if the market cannot clear the price P prime, which is located here, what happens? Your marginal revenue that you're getting from selling one unit is less than the average variable cost. It costs more for you to produce something than you can charge on the marketplace. So if your price is lower than P prime, the suppliers will just, stop producing anything. There's no point in producing something where it costs you more to produce it than the market price that you can charge for it. Right? So if price is less than P prime, then the firm will cease production. But if the price is between P prime and P double prime, so these are the two sort of broken lines here. So if the price is between this line and this line, the price is between P prime and P double prime, the firm can produce because they still make more money than their average variable cost. But in the long run, it cannot recoup its fixed cost. Right? What's happening is that, yes, the marginal cost of producing a unit exceeds the marginal revenue that they get out of it, but the difference isn't large enough for them to start recouping their fixed cost, the cost of building that factory. It's only when the price is over P double prime is when they can actually keep producing and still recover some of their fixed costs. Right? So that's the idea. And then supplier-supply curve is their marginal cost curve. So this marginal cost curve that I drew at the beginning in the red curve, that curve essentially dictates your supplier's willingness to sell. Okay? Questions about this? Okay. So let's talk some more about a perfect competition. The total market has a total supply curve equal to the sum of individual supply curves for the participating firms. Okay. So obviously, the total supply curve of the market is, you look at the individual supply curves of the participating firms. So these become sort of your short-run supply relationships. But in the long run, in a stable commoditized market, in the long run, all surviving firms will end up with the same cost structure and will be operating at optimum point where their average cost is equal to marginal cost and their profits will be basically driven towards zero. So that's what happened if you have a lot of competition. Your average cost becomes your marginal cost. You can operate, but your profits go down and down and down, basically driven towards zero. So this is what that relationship looks like. In the long run, all surviving firms will end up at that optimal point where average cost is equal to the marginal cost. Okay? So in the perfect competition case, your AC has to be equal to your MC. So this is the point. So this is the point where the firms will be operating. Average cost equal to marginal cost. So this is that point here as well. And this is the idea of the perfect competition, okay? So you don't have, so in perfect competition, the price that you set is not in your hand as a firm. The market sets the price. And then this is where you end up operating, where your average cost and marginal costs are equal. Now let's think about the other extreme, the monopoly pricing. In monopoly pricing, there is no competition. Supplier will set the price. So you're not driven by market forces because there are no competition. And in transportation realm, public transportation services and isolated toll facilities are similar to this. So remember, you're still subjected to the demand curve related constraint. Like, if you charge too much money, then people will just stop consuming, right? So there is going to be some elasticity that come into play. And the backward sloping demand curve will come into play. But you have no other competition. You don't have anybody who could come out and set their price at their marginal cost. Right? No other supplier is in the market. So now, because you're set to set your prices, you can adopt different strategies, and some of those strategies might include maximizing profit, maximizing revenue, maximizing net social benefit, or others. Okay, so let's think about what perfect competition might look like. So maximum profit still happens at when the marginal revenue equal to marginal cost, because see, this idea is still the same. Even if you have competition or no competition, maximizing profit still happens when marginal revenue is equal to marginal cost. But sometimes you might have other objectives, such as maximizing revenue. And some transit company may not want to maximize profit, but instead might want to maximize revenues. So maximum revenue happens when marginal revenue goes to zero. So remember, when we try to maximize any function, the function's maxima occurs when the derivative of that function is zero. And we know that the marginal revenue, when we talk about anything marginal cost, marginal revenue, we are talking about the derivative of that function. So we do want to, if you want to maximize revenue, you want to operate at a point where marginal revenue is equal to zero. Okay, so this is not, oh, this is zero. Now, you want marginal revenue to be zero if you want to maximize revenue. However, this you will run into the question of your demand then. Is your demand elastic or is your demand inelastic? Remember when we talked about if your demand is inelastic, then your marginal revenue is more than zero. Okay, so if your demand is inelastic, means epsilon is less than 1. Remember in the last lecture, we learned that if the magnitude of elasticity is less than 1, that means you have inelastic demand. Okay, so your marginal revenue is actually greater than 0. So you can raise prices still until you hit the point where your marginal revenue becomes 0. Okay? But if your demand is elastic and you still want to maximize revenue, your marginal revenue is less than 0. So if you take the derivative of the demand function and your elasticity value is less than or greater than 1, that means you have elastic demand. That means your marginal revenue is less than 0. So what you need to do to maximize revenue is lower the price. So it's not like in perfect competition, nobody ever lowers the price. If the demand is in fact elastic, then the supplier may still be forced to reduce the price if the demand is elastic. But if the demand is inelastic, then they won't be forced to lower the price. And then the last one, maximize social benefit. We'll talk about that a little bit later. But let's first understand this max profit and max revenue pricing. Okay. So what I'm showing you here, first of all, remember the axes. I'm going to go ahead and annotate this. So this is the Q axis, and this is the price axis. So you got the Q and P axis. And then initially you only have these two curves here. This is the marginal cost curve that starts at infinity and goes down. So this curve is the marginal cost curve. And then you have the demand curve. Okay. So the marginal cost curve and the demand curve. And let's also think about if your price function, and because remember, I'm telling you the demand curve is linear, backward sloping, but linear. So it's going to have an equation like P equal to A plus BQ. You'll see that. This equation is a linear equation, and then this demand function. Okay. So my R value, my revenue that I'm going to be able to generate from this is P times Q, the unit price times the quantity sold. And when I do P times Q, I just multiply this equation with Q. So this equation becomes AQ plus BQ squared. Okay. And then if I want to derive the marginal revenues, I take the derivative of the function, derivative of the revenue function. I just simply take the derivative of the revenue function. So I get dr over dq. I just simply take the derivative. AQ plus BQ squared becomes A plus 2BQ. And then this line, A plus 2BQ line, is this line right here. Okay. So this is my red line. I should probably say that here. So the red line on the curve is the marginal revenue curve. So if I want to maximize my revenue, I want to be supplying this amount of quantity. If I want to be maximizing my revenue, I want to be supplying this quantity, Q double prime, because that's where the marginal revenue curve hits zero. It's not the intersection of this curve and this curve, by the way. So we should be very clear here. We should be very clear that this is a different point. This point is a different point. It's not the key point at all right now. When you try to maximize the revenue, it's the point where the marginal revenue curve goes and hits the zero line. So it's a different price point from here to here. Oops. Okay. So Q double prime is not this point. It's not this. So this point is not Q double prime. This is not what we're talking. This is a different curve where the marginal revenue curve strikes the x-axis. And then obviously maximum profit curve. The maximum profit will occur where your marginal cost line hits the marginal revenue. Remember, the maximum profit one was marginal revenue equal to marginal cost. And remember, this is my marginal revenue curve, the red line, and then the green curvature is my marginal cost curve. So when they hit equal, that's my maximum profit one. So this is my maximum profit line. And then this is where that happens. And I can divide, this is Q. Okay, I think I had a little bit of an internet connection issue, but I think I'm back now. Can you all hear me? Okay. Sorry, I had to disable the share for a second because I thought I lost you guys here. Okay, but apparently I haven't. Okay, very good. Okay, welcome back. Sorry about this. I thought I got disconnected here for a second. So let me go ahead and share my screen. Can anybody tell me what was the last thing you heard? Can anybody update me on the last thing that you learned, either via chat or? Okay, so sorry about this. Can you guys hear me now? Give me a thumbs up, maybe. Something's going on. I don't know what it is. Can you all hear me? Okay, it looks like I'm back now. Sorry about this. So can you guys tell me what was the last thing you heard so that I can continue from there? Either via chat or via voice. Okay, so you did hear that. Okay, perfect. MR equal to MC. So let me go ahead and share the screen. So it makes sense that MR equal to MC for maximizing profit. So let me just quickly annotate this. So this first point, the first star point, is my MR equal to MC. So that's where the marginal revenue curve hits the marginal cost curve. And this becomes your max profit point. So this is the quantity you want to produce. And you go back, project that point back up to the, you project that point back up to the demand curve. So you can come up with the price that you want to charge. But if you want to maximize revenue, that's a different price point. To maximize revenue, you want to have the MR line, the marginal revenue line, hit 0. And that marginal revenue line is right here. It hits 0 right here. So then you can go back up to that Q prime, Q double prime, or Q star, Q double S point, and then project it back onto the y-axis. So you'll get your price point that you want to charge. Just want to emphasize here that this point is different than this point. Okay, so these two are, this point is not the same as this point. They look kind of close, but it's not a mistake that those two are different points. So the point, Q double prime point, is the lower point, and that's where you maximize revenue. This is a different point that we'll talk about later, where the marginal cost curve is the demand curve. Okay, so we'll talk about that somewhat later. But is this clear? How we kind of took the revenue equation, took its derivative, and then when that derivative hits 0, the marginal revenue hits 0, that gives us the maximum revenue point. And then max profit is where MR equal to MC. And we can define the prices based off of that. Any questions about this? Any questions at all?